Good afternoon, everyone. Today we are going to be in Chapter 2, Section 4, and this is just a little bit more on slopes. In 2.3, the last lecture, we talked a lot about slopes and slopes of lines and how to calculate that and how to do equations with that. And so today we're going to talk really about two special cases of slopes, and then we're going to talk about the average rate of change of a function, which is using slope, only you don't have a nice straight line. You're using a function which is wavy. So it's not a long day. I'll do one example of each, and then I'll work a big example on the back of the board, and that's pretty much it, excuse me. So first, let's talk about the two special kinds of slopes that we're going to talk about today. First, we're going to talk about parallel lines. Parallel lines are usually indicated by these two side-by-side slash marks, thus parallel lines. Parallel lines are two lines that run side by side that never cross each other. So you can think about them as two streets that run the same direction, like run north and south. If they are done well, like in a city, they will never cross each other, right? They're never going to turn, they're never going to intersect each other. Parallel lines do not cross. So parallel lines have the same slope. That's what's special about their slopes. The other kind of lines we're going to talk about are called perpendicular lines. Perpendicular lines make an intersection, like when you come to a stoplight and there's four ways. It makes a perfect 90 degrees or a perfect cross like this when those two lines intersect. And we use the little box in the corner to indicate a right angle. So those are perpendicular lines. Perpendicular lines are often indicated like this with this upside down T. That just stands for perpendicular. And perpendicular lines have negative reciprocal slopes. And you might be like, what in the world is a negative reciprocal slope? Well, I'm going to show you. We're going to do an example. We're going to just look at the slopes. So we have a line with a slope m equals 2. So the slope is 2 for our first line. So we need to know, or we want to know, what is the slope of a line that is parallel to that first line? Well, what did I say? Parallel lines have the exact same slope. So the parallel slope would be 2. They have the same slope. Now perpendicular has negative reciprocal. So negative means negative, and then reciprocal means you flip it. So if I wanted to write 2 as a fraction, how would I write it? Well, 2 is the same thing as 2 over 1. So the reciprocal of 2 is where we flip it. That would be 1/2. I took my top and I made it my bottom. So the negative reciprocal of 2 would be -1/2. So the slope of a line that is perpendicular to our first line would be -1/2. All right, let's do an example. Our instructions say to find a line parallel to y equals 2x plus 1 through the point -3, 1. So first thing that we need to determine is, first it's parallel. So we know we're finding parallel. Parallel means the same slope. So then what is the original slope that we are dealing with? Well, this is written in the y equals mx plus b form. That means our m is 2. So that means our parallel slope is also 2. So now we need a line through the point -3, 1 with a slope of 2. From 2.3, I'm hoping you'll remember a special equation called the point slope form. Point slope form was y minus y1 equals m times x minus x1. Hopefully you remember that because it was just the other day. So we have y minus, and then our y1, that's our point, we have 1, equals our new slope, which is 2, times x minus x1, which is a -3, so that becomes a +3 in there. I'm going to distribute my 2 in, so So I have y minus 1 equals 2x plus 6. Subtract my 1 over, y equals 2x plus 7. Here I have an equation of a line with the same slope as the original through the point -3, 1. And if I needed to graph that, I totally can, and I'm going to so I can show you what they look like. Okay, first I'm going to graph my first one. So 2x plus 1. That means I have y-intercept at 1, and I go up 2 and over 1 for my next point. Please forgive my maybe less than straight lines as I draw on the board. So this was the original one. Now we have our parallel line, 2x plus 7. So I have 1, 2, 3, 4, 5, 6, 7. Down 2 into the right one. My other point, shoop, shoop. So if you notice, minus my slightly wonky line drawing on the board, we have two lines. They look to be going at the same incline or the same slope, and they're parallel, so they're never going to touch. So that means we did a good job there. Okay. Now we'll do another example. We're going to find a line perpendicular to x plus 4y minus 8 equals 0 through the point 3, -5. So in our first example, it was really nice. We already had it in y equals mx plus b form. This time they didn't give us that. So first we have to manipulate our problem around to figure out what our slope is. X plus 4y minus 8 equals 0. Oops. I got chalk all over my feet. Okay. So what we need to do is we need to isolate our y. We need to get it in y equals mx plus b form. So I'm going to move everything over to the other side. So that's -x plus 8. Divide everything by 4. I get y equals -1/4 x plus 2. So the slope of my original line is -1/4. So then what is the slope of a line that is perpendicular? Perpendicular is where we have the negative reciprocal. So whatever the sign is, we do the opposite, and then we flip it. We make it a fraction and we flip it. Well, this one's already a fraction, so we just need to flip 1/4 towards 4 over 1, and then it was negative, so now it's positive. So our slope is 4 for our new line. Now we have a point. Now we have the slope. Now we're going to use the point slope form just like we did just a minute ago. Let me erase that a little bit. So I have y minus y1 equals m times x minus x1. Y minus my y1 is a -5, so that becomes a plus. My m is 4 times x minus my x1 is 3. Y plus 5 equals, I'm going to distribute my 4 in, so it's 4x minus 12. Y equals 4x minus 17. So I am going to graph these for you so that you can see that it does indeed give us a perpendicular line, albeit it's a crazy one. If you pull up my notes, my graph on there, I actually get to use like rulers and stuff. So my lines might be a little bit straighter than they're going to be. But I think you'll give me some grace here. So first I'm going to graph my first line, which was -1/4 x plus 2. So across at 2, I go down 1, over 1, 2, 3, 4. Actually, I'm just looking at my graph, and I think I did my graph wrong, but that's okay. I mean, on my paper. Ugh, that's not a good line, but that's okay. And then I have y equals 4x minus 17. So minus 17, then go up 1, 2, 3, 4, over 1. Oh, this is going to look really, really wonky. I'm sorry. I don't actually know if it crosses right at that point, so do forgive my picture. It might not actually cross right at that exact point. But if you look, I did get a cross, I did get an intersection, and it does make a right angle. And that's always true. Perpendicular lines always intersect at right angles or at 90 degrees. So those are the two special kinds of slopes. We have parallel slopes, which are the same. We have perpendicular slopes, which are negative reciprocals. Now we're going to talk about something that sounds really hard or mathy, but it's really not. It's really just finding the slope. So the first thing you need to remember that slope is the rate of change. It's what's going on. It's the rise over the run. It's what's changing. All right, can I get a little bit on there? Nope, I'm going to cut out the remember part. So just remember that. I want to get that graph in here. Okay. A lot of math words here. It's like I said, it's slope. That's all this is. The average rate of change of a function. So when we've been dealing with slope, we've been talking about straight lines. That's what we've been doing. Rise over run, what happens to our line? Well, we can use straight lines to figure out what's going on in a function that is not straight, okay? So here's a picture of a generic function. This whoop, shoop, shoop. We can draw what's called a secant line between 2 points, determine the slope of that line, and that kind of tells us the rate of change or the average rate of change of what's going on of that function in between those 2 points. That's what the average rate of change of a function is. So it says, let x1 f of x1, so this is x1, y1, and x2 f of x2, which is x2, y2, be distinct points on the graph of a function. So we have 2 different points on a function. They're not the same point. That's what that says. If that's true, if we have that, then the average rate of change of f of our function from x1 to x2 is f of x2 minus f of x1 over x2 minus x1. Notice, that's y2 minus y1 over x2 minus x1. We can find the average rate of change of our function between those 2 points by simply finding the slope of a secant line through those 2 points. Because I don't know what's really going on here at this bump, right? I really don't. But I can find the slope of my secant line between those 2 points, and that will give me an average of what's going on. Notice it doesn't tell me exactly where it peaks. It doesn't tell me what my low is or anything like that. But it gives me an average of what's going on that graph, which is very helpful when determining what a function is doing at a certain time. So that is what the average rate of change is. So we're going to do an example. It's actually 3 examples, but it's really just one. It looks like 3. Okay, so we want to find the average rate of change of f of x equals x squared from, then we have x1 equals 0 to x2 equals 1. We have another one and another one. So we're just going to find the average rate of change of this function on different segments as we progress. Okay, so we're finding the slope. That's all we're doing. We're finding the slope. So the average rate of change said that we have f of x2, or y, minus f of x1 all over x2 minus x1. Well, it gives us our x1 and our x2, doesn't it? But it doesn't give us our f of x1 and our f of x2. But that's okay because we have our function. So all we have to do is plug in those values to get our f of x's. Okay? So we have f of x2, which is saying f of 1 minus f of 0 all over 1 minus 0. Well, what is f of 1? If we plug 1 into our function, what are we going to get? Well, 1 squared, which is 1. If we plug in 0 into our function, we have 0 squared, which is 0. And that's all over 1. So we get 1 over 1, which is 1. So the average rate of change from 0 to 1 on x squared, on the function x squared, is simply 1. And I'm going to draw a very basic graph of, this is f of x equals x squared. This is what it looks like. So from 0 to 1, sorry, I wanted to make sure my graph is semi-accurate. 1, 2, 3, 4. Okay, so here's a very basic graph of what f of x equals, like what it looks like. It's a quadratic, it's a parabola. So it does this. And so what we just found is that the average rate of change in this function from the point 0 to 1 is about 1. So the slope, if we could find the slope of this curved section, it would be about 1. And we would use a secant line just like we drew over there. Okay, so let's see what happens from 1 to 2. Again, we're finding the f of x2 minus f of x1 over x2 minus x1. So that would be the f of 2 minus the f of 1 over 2 minus 1. Well, f of 2 is 2 squared minus 1 squared all over 1. 2 squared is 4 minus 1, which is 3. So there's an average rate of 3 if I go from 1 to 2. Well, if you look, here's 1 and here's 2. Look at how much steeper that is than it is over here. So that makes sense that our average rate of change is going to be that much greater. Let's do one more. Is going to get to stay in there or not? It does not. That's okay. I can take you back over there to see the picture. So now we're going to do the exact same thing, but we want to see the average rate of change from -2 to 0. Again, you're just finding the slope. F of x2 minus f of x1 equals x2 minus x1. F of x, of 0 minus f of -2 equals 0 minus a -2. So f of 0 is 0 squared minus a -2 squared all over 2. Well, you have a -2 squared, which becomes a +4, but we have that negative out front. So that's -4 over 2, which is -2. So we have an average rate of change of -2 on that interval. And if we go back and look at our graph, sorry, I hate to move you around so much, but it is what it is when we're doing virtual. So if we go from -2 down to 0, that's a big change. And notice it is a negative slope. If we had a straight line going from this point here down to there, it's telling you the slope of that line would be -2. So the average rate of change, it sounds scary. You're just finding the slope. It allows us to figure out what's going on in a function that is not a linear function, thus, has rounded corners and curves. And that's what's nice about it. So that is section 2.4, the section on more slopes. If you're still not comfortable with slopes, go back to 2.3 and play around with it. And you can always email me if you get stuck. I hope you have a good day.